Good afternoon. Welcome to the University of Manitoba Alumni and Friends Virtual Learning for Life program Climate Series. My name is Tracy Bowman, and I'm the Executive Director of Alumni Relations at the University of Manitoba and a very proud alum. Before we begin, I'd like to acknowledge that the University of Manitoba campuses are located on the original lands of the Anishinaabe, Cree, Oji-Cree, Dakota, and Dene peoples, and on the homeland of the Métis Nation. We respect the treaties that were made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So thank you everyone for joining us from wherever you are around the world and making this event part of your day. We're able to offer this program free to all of our alumni and friends, thanks to the very generous sponsorship of our affinity partner, IA Financial Group. Many thanks to them. You can learn more about the insurance options that they offer alumni on the alumni website. So before we begin, just a few housekeeping details. This session is being recorded. You're all watching it on YouTube, and we post it on our website about a day or so later. So you're able to view it as many times as you'd like, as well as share with friends and family. I encourage you to go to our website. We have over 35 sessions over the last 2 years that we've conducted. So lots of really great content on every topic imaginable with some of our amazing researchers and professors. There will be time at the end of our presentation for questions. So if you've been with us before, you know the drill. There are two ways that you can ask questions. We use the platform Slido. That's www.slido.com. And today's password is VLFL30. So you just enter that in there and then you're able to post a question that way. The other way, if you prefer, is just using YouTube. You'll see there's a chat under where you're watching it, so you can ask questions there, and we'll go back and forth between Slido and YouTube. So I really encourage you to ask lots of questions. Our speaker will be able to make that time at the end. And if we don't have time to answer all your questions, we'll make sure to find a way to provide you with answers to all your questions. So I'm really delighted to introduce today's presenter. I know you're going to find this topic fascinating. Today's presenter is Dr. Michelle Mcchrystal, and she will be presenting on the topic of a wetter future for the Arctic. So let me tell you a little bit about Dr. Mcchrystal. She's a postdoctoral fellow at the Center of Earth Observation Science here at the University of Manitoba. After completing her PhD studies at the University of Cambridge and British Antarctic Survey, where her research focused on understanding the tropical drivers of Arctic circulation, she then went on to do a postdoctoral research position at the University of Exeter, also in the United Kingdom, where she assessed how changes in tropical oceans impact Arctic sea ice and temperature. In her current role at the University of Manitoba, Dr. Mccrystall is researching future changes in Arctic climate with a very specific focus on how precipitation is projected to change in the future using global climate models and the impacts that these changes will have on local people and environment across Canada. Now, you may remember Dr. Mccrystall released a paper at the end of last year of 2021, and it garnered quite a bit of media attention. So you may have read a little bit about this in the Winnipeg Free Press. So I'm really excited to introduce. So Dr. Mccrystall, you can take it away and share us your presentation.
Great. Thanks very much, Tracy, for the introduction. So I'll dive straight in, as hopefully everybody can see my presentation slides here. So as Tracy said, I'm a postdoctoral fellow here at the university. I've got a few years experience working in this area, but over this last 2 years, so I've been here for about just over 2 years, and within this time, I have been focused on changes in precipitation to the Arctic. Hence my title, A Wetter Future for the Arctic. And I first want to acknowledge my supervisors and my co-authors that helped me on this project. So Julianne Struva, who is a professor here at the university, as well as Mark Serez, Bruce Forbes, and James Screen, who is a previous boss of mine back in the University of Exeter. So I'll just start at the very beginning. We obviously live in quite an Arctic environment, especially at the minute when it's pretty cold outside today still, even though we are in technically spring. So you're probably very well aware of the Arctic climate and really how the Arctic climate is changing a little bit. But to sort of take it back to real basics, we define, or sort of scientifically, the Arctic is defined as a region anywhere above 66.5 degrees north, 60 or 70 degrees north. And it is most probably famously known as that you have 24-hour darkness in winter and then 24-hour brightness in summer. And I think I've got that wrong on the slides there. I forgot to put it right. But basically, at winter time, we get complete darkness. Summertime, we get complete sunlight. And obviously, that filters down throughout the latitude. So we have darker winters and lighter summers here. And as you can imagine, sort of based on that, the fact that we do get continuous darkness in the winter, or when the winters in the Arctic are pretty cold, and the summers are therefore a lot warmer, because you get continuous daylight. So I've made sort of just a very simple plot here to show, yeah, it's cold in winter, it's warm in summer, apart from Greenland, which is kind of always cold, obviously because of the fact that it's a massive ice sheet. And sort of, so my real interest is on the precipitation. And this bottom sort of figure here, hopefully you can see my red pointer, is showing the average precipitation. So this is all precipitation over the Arctic in wintertime and in summertime. And we actually get more precipitation in summer than we do in winter, because winter is a lot colder. You won't get as many storms, things like that, that maybe get into the Arctic. There'll be a lot of convection sort of driven throughout the winter. So summertime, we will get a lot more precipitation. But as I've said sort of at the start, and I just want to talk a little bit about the issues that are sort of happening in the Arctic and why we're really interested in the Arctic, is the fact that the Arctic is changing very, very rapidly. So some of these figures here I'm showing are actually to exemplify the fact that the Arctic is warming twice as fast as the rest of the planet, and that's termed as Arctic amplification. This figure here on the left in the black was done by Zachary Leib. And in this, he is showing the temperature anomalies. So basically, the temperature difference relative to a background mean. So this is taken from a baseline from 1951 to 1980. So basically, any differences in temperature from that baseline. And as you can, I think, really nicely see, over this last 20 years, there's been a real increase in temperatures across the Arctic, especially considering compared to the rest of the world. So the rest of the world is showing these Arctic, temperature anomalies, but they're most prevalent in the Arctic. So you're getting a lot more warming in the Arctic. And this is looking at sort of year round, but we can break this down to seasons and show that a lot of this change is really happening in autumn and in winter. We do see it also as well in spring, but the kind of main seasons for this is in the autumn time and in the winter time. And some of the reasons for that is this change in sea ice. So I'm sure you're probably well versed and know a lot about the fact that the Arctic sea ice is declining. That's one reason as to why we are getting a warmer Arctic, simply because when the sea ice melts, you're left with all this open water across the Arctic. And when there's a lot more sunlight in the summertime, the oceans warm up. But then what happens in wintertime, whenever we go into autumn and winter and there's a little bit less sun, and the sea ice will start to refreeze back, the heat that the ocean has stored is then allowed to sort of flow back into the atmosphere. So basically you're getting all this heat that's been stored for about 3 or 4 months is being pushed back into the atmosphere and causing this increased warming. So sea ice decline is very important for many reasons, but one as well because of the fact that it's increasing the warming across the Arctic. So here's just some examples of how much the sea ice is declining. And this is looking at September. So we will get minimum sea ice in September time. So as you can see here, I think it's a very simple trend. So this is looking at sea ice extent trends from 1979 up until 2020. And of course, we get a lot of variability year on year, but the general trend, which is shown in this blue line, just shows there's a complete decline of sea ice over this last 30, 40 years, which is at about 12.7% per decade. 2012, so if we look at this figure on the right and this red dashed line, that's the sea ice extent for 2012, which is the lowest it ever was, which is at about 3.14 square kilometers across the Arctic. That was the extent. And I've shown a few of the other years, for example. So the blue line here is where we currently are. We are technically currently below that 2012 line already. But of course, as I said, and I've sort of shown here previously, there's a lot of variability within that. But basically, as I show here, over those last 15 years, so from 2007 to 2021, we have had the lowest 15 years of September sea ice extents on record. So I point out here 2005 and 2006, and those are the 2 years where that's showing that everything below this, which is where we currently are, is much lower than those means. So year on year, we are getting a lot less sea ice in the Arctic. And this is then again looking at these anomalies of the sea ice in the Arctic. And this first figure is looking at the sea ice anomalies, excuse me, in September of 1981. So where it is red, it's showing that there's a anomalously less sea ice, and whereas blue, it's showing that there's more sea ice. Excuse me. And if we compare the sea ice extent in 1981 to 2012, which was the lowest year, if you remember, you see there's a lot of red. And basically this means that this is where the sea ice has been lost. And they say that it's about the size of Alaska, which I've kind of highlighted here. So basically the size of Alaska, we've lost that much ice in the Arctic. This is the same size of Alaska. So basically we're showing where there's a lot of ice being lost in the Arctic. Now that's just sort of some background on kind of the main challenges and the main things that are happening with the Arctic. But as I've said, precipitation. And although we can see that there's been changes in temperature and in sea ice over the observed record, so up from like 1970 to now, so we usually go back to 1979 roughly, because that's when satellites really became prominent and we got a lot of information on our weather and climate from satellites. So that's kind of our most robust record, shall we say. But in terms of precipitation in the Arctic, we're not seeing the similar sort of trends. We're not seeing this increase in the same way we're seeing more a greater warming and less sea ice. So some studies have said that in the data that they had looked at, that there is this increase. So this is looking at these top figures here. So I know there's a lot of lines around here, but hopefully I'll walk you through them as best I can. So again, hopefully you can see my red pointer. But in this, you can see these are looking at observed. So the actual observations that we're getting from weather stations, from little buoys in the oceans. They give us a lot of temperature data of the atmosphere, and from ship measurements, everything as well. So all our observations were taken in, and showing here that in some of these observations we do see this increase in precipitation from around 1950 to 2000. And he was showing this as well, or they were showing this as a paper by Rawlins et al. So Rawlins and a group of people back in 2010. And they were showing as well that in some model data, you do see this increase in precipitation. However, more recent studies, so a recent study done by Barrett et al. In 2020 and Bozabert et al. In 2018. Again, this is looking at what's called reanalysis data sets. So quickly to explain reanalysis, as I said, we've got a lot of observations, but also in the Arctic, we have problems with that. And I show that here because we get a lot of uncertainty in the Arctic. And one of the main reasons is why, and hopefully you can kind of guess based on this image, is the fact that we don't have a lot of observation stations in the Arctic, especially compared to the rest of the world. So you only have, if we look at like southern Canada into America, across Europe, parts of Africa, it's basically all green. That's all the weather stations that there are. We don't have as many in the Arctic. So therefore, what we do to try and counter that in many ways is to in the regions where we don't have a lot of observations, we use models to try and interpolate the data between that. And that's what we're using here. These are called reanalysis data sets. So we're using our observations, but then using models as well. We take them as our best kind of observations of, especially of precipitation in the Arctic, because we have observations, we have models, we're marrying the two together and we're getting a much more robust data set. And basically when we use these data sets, we see that there isn't really an increase in precipitation. So sort of going back to this, so that's one of the reasons why we have so much uncertainty. So as you can see, there's a lot of variability, a lot of ups and downs within these model data sets, within these observation reanalysis data sets. But basically there's been no positive trend in precipitation. And some of the reasons could be that we're not getting a lot of the precipitation. We're not really getting a robust understanding of how much precipitation is really falling because we don't have enough station data. And some of the reasons for that, as you can imagine, the Arctic is a very harsh terrain. It's very difficult to get to those regions. We have obviously a lot of sea ice in the area, so you can't easily get there. We also have very curious animals. My boss had recently went on an expedition to the Arctic and found polar bears were sniffing around their equipment and like didn't break anything, which was very lucky, but sometimes they can actually on the stairs or on the and then to get to these regions because of the harsh terrain, but also if you've got extreme weather, if you've got like an extreme cold day or a snow blizzard, it's really difficult to get to these locations. So therefore, there is some uncertainty in our precipitation observations, but we have amazing models that give us a really good understanding, even in spite of this. So while our observations there, they are good. I know I'm probably maybe saying that they're not good, but they are very, very good. We just would like more, essentially, just to really make this a very robust understanding. While we don't see much trend happening in the observations, what studies have shown is that we're actually going to see this huge increase in precipitation in the Arctic in the future. And so this top figure here of like the blues and greens and browns color is showing precipitation change by 2016 to 2035 or 2081 to 2100. And this is taken from a report called the IPCC Climate Change Report. The IPCC stands for the Intergovernmental Panel on Climate Change. And basically, the IPCC, they are tasked sort of every 10 years of collating all of this climate information of everything to do with climate across the whole planet, not just the Arctic, but in terms of everything to do with climate, and get the latest research and really try and understand as best we can, basically taking all of the research that's been done on climate change, what's the state of the climate now, what's going to be the state in the future. And these are based on climate models. So I'll talk a little bit about what climate models are in a minute, but just to sort of show these future precipitation changes that based on these climate models are showing that by the future, so by 2081, 2100, by the end of the century, and this is looking at two different studies, between 50% or 60% increase in precipitation. So as you can see here, this dark blue relates to this 50-60% increase of precipitation in the Arctic in the future. This is also shown in another study by Bentanja and Selton back in 2014, where they've shown, so again, looking at the reds, that's about a 60% increase in precipitation across the Arctic. So we're seeing that in the future, and this is looking at the end of the century as well, so 2090 to 2100, the very, very end of the century compared to the start of the century. And basically, one of the issues of this is as well is the fact that, okay, we're getting more precipitation, but actually a lot of this precipitation is changing insofar that it's falling more as rain than as snow. And that's what this figure here is showing. So you can see in the blue, we're seeing snow, and we see in the red, we're seeing rain. And this is looking at a difference. So basically, and this is looking, say, from June, July, August, September, October, November, we're seeing that within that sort of end of summer, autumn, going into winter period, a lot more of the precipitation is falling as rain than falling as snow. And that, of course, will have huge consequences. So I said, I'd kind of backtrack a little bit. I just want to talk briefly about what a climate model is. I'm sure there's people probably are aware of this, but just to kind of really explain this, hopefully in a very easy manner. As you can imagine, trying to understand the whole climate system is very tricky. So we have to try to break it down. As I've said, we do have good observations, but we also want to see how things really work within the climate system, or we want to see how things change in the future. So for that, we need to have a model. We need to sort of be able to break down all the processes that happen within the climate system. And in the first order, the way we do this is we break down the entire planet into this sort of system of grid squares. So like we follow lines of latitude and longitude going sort of from the North Pole to the south, and we break up the whole atmosphere based on that. We also break the atmosphere down into vertical columns. So as you know, the atmosphere just isn't one layer, it goes the whole way up to about, it extends obviously into outer space essentially. So we have to model that because all of those, there's so many interactions kind of happen both in a horizontal plane, but also in the vertical plane. So we need to model that. So we break that down into grid squares as well. We also break it down in the ocean. So we go down as far as we can in the ocean, because all of those processes all impact the atmosphere, all impact the ocean. And sort of some of the processes that we have to sort of model within this is, air exchange, how clouds are formed, the water cycle, the carbon, how solar comes in. So there's a lot to really sort of compose within this. So that's why we do it. We break it down by grid squares. It's a lot of mathematics involved. People that much more intelligent than I years ago designed these climate models based on these sort of fundamental fluid dynamic equations, essentially. Basically tell us how the whole atmospheric system works, how it interacts with one another, broken down into these grid squares. So CMIP, I'm going to talk a lot about CMIP. So CMIP stands for a Coupled Model Intercomparison Project. And basically all that CMIP means is that we're taking, just if you imagine these are all different models, and we're taking multiple models from all across the world and just comparing them. So we have around, say, 30 modeling centers around the world, so in all corners of the world, and even some model centers have a few different models in themselves. And we break and we compare them. And it helps us to paint a much better picture of climate. And the way that I would sort of describe what we're doing and why we're doing it and why we have these coupled modeled projects is, for example, if you took 10 chefs and give them the same recipe, each meal will be slightly different. You know, like one chef might have maybe more salt in it or might cook it longer or shorter or something, and it'll just taste slightly different. But if you took those 10 chefs together and they all cook the same meal, you're going to get an even more amazing meal than you ever thought possible. And that's it's probably a very weird analogy, but it's the easiest thing that I can think of to kind of explain, you know, what this CMIP is and what this coupled model, and the reason that we're doing it is to get a much better, more holistic understanding of how the climate works as now and how it's going to change into the future. And so, as I said, I've talked the previous models. We're currently on this CMIP 6 project, but we've had previous CMIPs before that. And kind of what happens with each iteration of CMIP is we're getting, you know, better models. So this is looking at models sort of going back in these sort of stages of these CMIPs. So this is like looking at the very first kind of model comparison, and as you can see, it's very coarse resolution. We're getting a higher resolution with the second, this is the third, this is the fourth, and as you can see, you can start making out now, this is looking over Europe. You can see Ireland and the UK, parts of Europe, Scandinavia, Greenland and Iceland. So as you can see, every iteration of this, we're getting better models, and as we get better models, we're getting better understanding of the climate. And so for our projections and how we resolve all of these systems are actually getting better every time. So we try and update this every couple of years to really get a better understanding of how the climate is changing. But as I said as well, we also look into the future with these models, and we do this based on a range of different scenarios. So we obviously don't have a crystal ball. We don't know how the future is going to change. So people who work in this kind of area in terms of the policy side of climate, they break it down into what might the temperature be, or what might the changes be if we have, say, no climate policies, for example, here, or you have some policies, or you have the Paris pledges, or even, like, for example, trying to stay within this 1.5 degree world, which I'll talk a little bit about later as well. So we take all these scenarios and we run our models with, okay, if we had no scenario and just let everything manifest as it is and we make no changes, or okay, we're going to have some changes, or we're going to have drastic changes. So you kind of have these different scenarios, and that's very important when we're looking at future climate change. So hopefully that kind of will set the stage for what I talk about now and give you some understanding of what I've done and why I've done it. So the work that I have done is to try and understand and assess these precipitation changes from that last iteration of this CMIP, which was CMIP 5, so it was the 5th project of CMIP, and compared to this current version, which is CMIP 6. And basically what the few starting questions we give ourselves was like, well, do the models do a good job of replicating precipitation? Are future predictions going to change from this newer set of models? And will there be greater changes to the precipitation type? So will there be more rain in these newer models? So the first question we kind of looked at was to see how the CMIPs really perform relative to the models, relative to the observations, sorry. And so these figures on the left-hand side here, so A and B, they're looking at, A particularly is looking at precipitation change. The blue is looking at observations, which is this reanalysis. And we can see that the models both are sort of following the same trajectory. They're within the same range of this ERA 5. So that's the type, that's the name of the data set that I use to do that I look at my observations with. There's another data set called GPCP, which is the Global Precipitation Climatology Project. acronyms of climate, or sorry, precipitation across the Arctic. So therefore we tend to only stick and focus on this era 5. But if we look at the spatial changes, we can see that the models which are here in CMIP 5 and CMIP 6 do a relatively good job relative to the observation. So where we see less precipitation in the Arctic Ocean and more precipitation as we go around the edges. And as you can see, most of the precipitation happens within the Atlantic side. So as you can see, here's Greenland, here's parts of Europe, Iceland, and so we're getting most of our precipitation occurs there. What I want to point out as well is this figure here is, and this is what I've termed as the snowfall ratio. And basically what that means is how much of the precipitation is falling as rain versus is falling as snow. So when we're in our higher numbers here, so like 0.8, for example, that means that 80% of the precipitation is falling as snow. When we get down to 50, it means that more of the precipitation will fall as rain. So at the minute, most of the precipitation across the whole Arctic is falling as snow, but that is decreasing, meaning there is more rain occurring in the Arctic. And this has already been shown by some studies. So looking over this region here at Svalbard, we can see that this is looking at liquid precipitation, and basically what they're showing is that there's been this increase in liquid precipitation, aka just rainfall, over Svalbard since sort of the 1980s. And looking at the bottom figure, there's been a decrease in solid precipitation, which is snowfall, between this decrease over this time since about 1990 onwards. So basically showing that actually in some observations we are already seeing this transition, this change to a more rainfall dominated precipitation, which is really one of the focuses of my work. So now, as I said, I'm comparing these two model data sets. And basically what this figure is showing, there's a lot of lines, I'm aware, some of them overlap one another, but basically what this is showing is that there is going to be a positive trend in precipitation in the future, which we already know, and that occurs in all seasons. In summertime here and in autumn time, we actually see a decrease in snowfall. So this is relative to, like, again, this background mean. So it's the anomalies relative to a background climatology. So how things are going to change relative to, a starting point. And so basically we're showing that relative to the starting point, we're going to see a decrease in snowfall in summer and in autumn. And what I really want to point out, what's really sort of most evident and most crucial to my work, is the fact that these changes are exacerbated within CMIP 6. So if you look at the solid line here, so if we look just at autumn, so figure D at the very bottom right-hand corner, if we follow this solid line, we're seeing that there is this significantly greater increase in the CMIP 6 rainfall than in CMIP 5. So the dashed green line, which I know is a little bit difficult to see, we're seeing that there is this huge difference between this increase in rainfall in the future. So by 2100, we're going to get a lot more rainfall in the CMIP 6 models than we are in CMIP 5. And if we look at this nice, what's called Velen plot here at the side, you can see that even more evidently. So the black line is the average between these two data sets, and the average for CMIP 6 here in the blue is much higher than in CMIP 5. So as I said, when we're looking at future climate scenarios, we have a range of different scenarios. So this is looking at the worst scenarios. This is very little climate policies are enacted, and so where the greatest change will happen. But even if we look at the medium case scenario, we still see the same kind of results. We're still seeing that there's going to be this increase in precipitation throughout the 21st century, that it's going to be dominated by an increase in rainfall and a decrease in snowfall. In certain seasons, we're still going to see an increase in snowfall in winter. And that's obviously due to the fact that in wintertime, we're still going to get minus temperatures. We're still going to get very cold temperatures because we get no hours of sunlight. So it's going to be cold. And if there is precipitation, it will likely fall as snow. But basically, the changes are still more prominently in the favour of CMIP 6. In the negative, obviously, the fact that we're seeing more rainfall in CMIP 6, as you can see here in the autumn time again, and less in the CMIP 5 models, and again, also less snowfall in CMIP 6 compared to CMIP 5. So basically what this is showing is that across the entire Arctic, so this is just like an Arctic average, we're going to see more rain and less snow in the future. As you know, the Arctic is a huge place because it's a body of water covered in ice and then surrounded by a continent, surrounded by land. So spatially, there's going to be a lot of differences really occurring. And so this is looking at breaking it down into each season again as well. So I break this down to look at each season because each season is very acutely different to the previous season or to the next season. And basically what we can see, so if we just look, so what I've done here is to take the rainfall and snowfall. So I've broken down the precipitation to the two forms and to see what the change will be by the end of the century. And so to do that, I take the difference between 2091 to 2100 and I subtract that from 2005 to 2014. And essentially what that is showing is the blue here is showing that there's going to be much more snowfall, or there's going to be an increase in snowfall at the end of the century in CMIP6 and less snowfall over the Central Arctic, and less snowfall over, this is going into the Barents Sea here, up around Svalbard, along Greenland, and also like near parts of Alaska and parts of Siberia as well. But we can see that this is coupled with like this huge increase in rainfall. So the blue here means that it's positive and the red means negative. But we can see in the autumn time, there's a lot of red, basically meaning that there's going to be a huge decrease in snowfall across the whole Arctic in autumn time. And then if we look at that in terms of rainfall, we're going to see basically that's going to be converted into rainfall. So by the end of the century, the whole Arctic is seeing this huge decrease in snowfall. So these negative temperature or negative precipitation values, and that's going to be replaced by this positive rainfall. So basically showing this transition on a whole spatial scale. And what's really most interesting about this is looking at, we take then the difference between the CMIP5 and the CMIP6 models. And essentially what this is showing is that over, again, this region is called the Barents Sea. We're showing that there's going to be a significant decrease in snowfall over the Barents Sea here, and a significant increase in rainfall. So this nice blue sort of highlighted by the dashed lines to show that this is statistically significant changes, that we're going to see the significant increase in rainfall all across the Arctic, all across the Arctic Ocean. Changes are greatest in autumn time. So that'll sort of be a prominent theme of what I talk about throughout this next 20 minutes, I think. We do see this significant decrease in snowfall again all across the Arctic. As you see in wintertime, it's only in this region. We see actual regions that there could be an increase in snowfall, which could be a positive for sure. But across the autumn time, across the whole Arctic Ocean, parts of the Canadian archipelago, northern Canada as well, and into parts of Northern Europe, Russia, Siberia, we're going to see this decrease in snowfall, which will be replaced by this increase in rainfall. So basically showing that in these newer models, we're seeing this greater increase in rainfall and a greater reduction in snowfall. I also do show the other seasons, the springtime and the summertime. And again, you can see that there's going to be decreases in snowfall where the red is. And in the rain plot, we can see there's going to be an increase in rainfall and the similar as well. So basically where there's going to be regions of decreased snowfall, that will be replaced by an increase in rainfall. And again, this is looking at this sort of worst case scenario or this top case scenario, which is one that climate scientists, we always tend to use because it's showing how much things can change essentially. I don't say how bad things can get because that's technically wrong, but just what the most change could be if we don't sort of enact change. But even if we look at these medium case scenarios, again, we can see in the autumn time that we should see this huge increase in rainfall. Again, in winter time as well, we're seeing these positive red values showing that there is this increase in rainfall. And with these blue values here, we're seeing this decrease in snowfall. So even lesser emission scenario, these changes will still very much happen. So what are the causes of this precipitation change in the Arctic? So there's kind of, I would say, three sort of main changes of precipitation change. And the first, and this is kind of actually under the umbrella of moisture, would be sea ice loss. So this figure here, I know there's a lot kind of in it as well. And this is looking at all different models based on this CMIP5 model data set. And basically what that is showing, so it's breaking down how much precipitation will increase and what is the contributing factor to that. So in the red, it is showing that in these models, the precipitation change is going to be mostly driven by this evaporation, which is due to sea ice loss. So as you can imagine, you lose sea ice, you're getting much more open water. And essentially that just means that there's a bigger pool of water to evaporate, to therefore have more water vapor in the atmosphere, therefore allowing a greater increase in precipitation across the Arctic region. There is also this change in transport. So basically, if you think of a storm, like of a weather storm, you see the rain pattern coming across, and that happens as well. So into the Arctic, you're getting these storms and other sort of planetary phenomenon, as it were, that brings this moisture into the Arctic. So it's driving it northwards into the Arctic, and that's called the meridional transport or moisture transport. So like storms and things like that drive more water into the Arctic region. And basically what this is showing is that, so if we look at this top plot, we're seeing this increase in precipitation, which I've talked about before, and that most of it is contributed to this increase in evaporation, so a local source of moisture. But we do also see that with this increase in transport of moisture into the Arctic, that also contributes to an increase in precipitation. It's more to do with the variability, so like the day-to-day changes, because as you know, storms don't happen every single day. So like today we don't have a storm, yesterday we did. So it's things like that. So that will bring in different, it'll have a more variable sort of stance on the change in precipitation. So those are the two, as I said, the moisture sources of the Arctic that will actually create more water within the Arctic. But this transition to a more rainfall dominated would actually be likely due, well, temperature change is kind of one of the key things that drives a lot of this. So if we have warmer temperatures, we're going to get more evaporation, for example. So therefore, those two coupled together, so less sea ice, a greater warming, creates more evaporation. But also when we have warmer temperatures, it means that a lot of this precipitation will fall as rain rather than snow. And basically that's what this is showing here. So the red is showing that, again, this contribution of precipitation into the Arctic based on all these different models. And most of it, because you can see most of the bars are coloured in red, meaning that this change to a rainfall precipitation in the Arctic is really driven by these local changes. So hopefully that kind of explains the main reasons as to why precipitation is changing in the Arctic. And then our question sort of based on that is, well, why is CMIP6 so much larger than CMIP5? And for this, there's actually two kind of main reasons as to potentially why this could be. And the first would be the sensitivity to warming. And essentially all that means is that for every degree of warming, is there more or less rainfall? Okay, so if we get 1 degree warming, in the old models, you might only get a 3 millimeter increase in rainfall, but with these newer models, you might get maybe 6 millimeters increase in rainfall with this 1 degree. And basically, and what we can see from this, so this is looking at global temperatures, this figure B here, and I've highlighted in green kind of the sort of main areas I want you to focus on. The blue here is looking at the CMIP6 models, and the orange is looking at the CMIP5. And again, if we look at the solid black line, I know this is probably difficult to see. If we look at the solid black line, we can see that it's much higher than the solid black line within the orange violin side, basically showing that, yes, what I've just said is correct, in that per 1 degree of warming, we get a greater increase in precipitation in the CMIP6 models than in CMIP5. And as I've said before, a lot of the changes that really occur are really happening within the autumn period and the greater changes in CMIP6. So one of the contributing factors could be the fact that within this season, within these months, a greater warming means there's actually going to be more rainfall, greater transition. The other reason, which kind of goes back to the main drivers of precipitation change, is the fact that actually in the CMIP6 models, we're seeing a much greater warming. So figure B here, the middle plot, shows the temperature changes at the end of the century. So again, this 2091 to 2100, that 10 years at the end compared to the 10 years at the start of the century. And again, the blue is CMIP6 and the orange is CMIP5. And again, looking at the solid lines in the middle, we can see that there's going to be a much greater increase in temperature across the Arctic in the CMIP6 models compared to CMIP5. So this is at around, say, 15, 16 degrees Celsius compared to 11 degrees by the end of the century. And actually some models within CMIP6 even show that there could be a 20 degree, 22 degree increase in temperature in the Arctic compared to about 17 within the CMIP5 model. So basically, we're seeing much greater warming within the Arctic. And this is evident across all seasons as well. So you can see it in springtime as well. So all those solid black lines are greater than the same of 5 models, showing that there is, across all seasons, greater warming. But as well, the idea of this increase in moisture, we see that as well in the same of 6 models. So this is looking at open water. So we're seeing much more open water in same of 6. So about 11 million square kilometers more open water in same of 6 by the end of the century compared to around 7. So there's quite a sizable difference there between the same of 6 and the same of 5. So when we have much less sea ice in same of 6, we're going to have a much greater pool of water to evaporate from, and therefore have much more precipitation on account of that. And again, this is evident across all seasons. As well, we look at what's called the vertically integrated moisture flux. Essentially just means the moisture that's going into the Arctic. And you can see again, especially in the summertime, that there is going to be a greater increase in moisture into the Arctic. So basically, it's kind of a 3-pronged approach, that we're going to get warmer temperatures and more moisture due to increase in moisture flux, so increase in water going into the Arctic, and this decrease in the sea ice, meaning there's much more water to evaporate from. And this, to really show that the relationship between the two, we look at this and we compare the temperature, the water, and the moisture flux to rainfall and snowfall. So the red is always rain and the blue is always snow. And as you can see in both, red is always, the blue is either sort of not really changing or actually negative, especially in the autumn time. As I said before, the autumn's where greatest change occurs. It's basically showing that yes, when we get warmer temperatures, we're going to get precipitation. When we get more open water, we're going to get more precipitation as well. So basically, that's all this is showing, that this positive and sort of negative relationship to in rainfall and snowfall. And as you can see, so these solid red dots are the same of 6 models, and the sort of less red or the muted red X's are the same of 5 models. So basically, we're showing here that we're going to get greater warming in the same of 6 models, so therefore we're going to get much more precipitation on account of that. So just showing that these relationships are important and are significant. I'll quickly try and finish up here as quickly as possible. We also are really interested in, when people often ask us, well, when are these changes going to occur? When is this going to impact me, and how is it going to impact me? And what we decided to do as well is to see, okay, in what decade because we can't really say like a definite date time or whatever, because that's kind of too ambitious, and our models aren't good enough to kind of give us like a very pinpointed thing, and there's so much variability. So we look at the decadal change, and essentially what we see here, so as I said, in this winter and springtime, by the end of the century, it'll probably still be snowfall dominated, just due to the fact that we get 0 sunlight hours, so it's going to be colder, so snowfall will dominate. But you can see that this is looking at this snowfall ratio, so the percentage of the precipitation that is either snowfall or rainfall. So anything above this line is more snow, and anything below is more rain. So we can see within this blue line, which is like decreasing much more rapidly than orange, that there's a much more rapid decrease in snowfall in the same of 6 models and in the same of 5. You see that in all seasons, and in the autumn time is when we actually should see this transition. So this is Arctic wide. So this is taking the whole Arctic region and taking an average, and basically is showing here that we cross this sort of threshold line, this 0.5 line, in around 2060, say, for the same 6 models, compared to about 2080 in the same of 5 models. So basically, so showing that there's this earlier transition to a more rainfall dominated precipitation of about 10 or 20 years. When looking at this spatially across the whole Arctic region, there's a lot of variability. So again, showing in wintertime and in springtime, we're seeing a lot more of this is actually going to be snowfall dominated. But if we focus down to the autumn time, we look at all these funky colours. The dark blue meaning that it's going to be still snowfall. So if we compare the central Arctic here in figure K, where hopefully my pointer has been seen, we can say that that is still in the dark blue compared to the same of 6 models, where it's actually gone into green. So you're getting again a change of about 20 years. You can see it more evidently here with the darker blue, showing that there should be this maybe 20-year change. So showing that where we've initially thought that these changes might happen in 2100 actually could be happening in 2080. So this 20-year shift of these changes. And as I said at the start, you know, we want to try and sort of enact change as much as possible, and I think science and the science I do should be sort of to go towards policy and try and enact policy changes and stuff, and to show the need and the necessity to live within the limits that our politicians are sort of set out. And what this is showing here is that I break down the Arctic into different regions, so like the land regions and the ocean regions. And basically what this is showing, so as you can see, the blue line here is where we have this transition to a rainfall dominated. And for these areas of the Arctic, in a 3-degree world, which is what we're currently on a trajectory towards, they will have transitioned to a rainfall dominated precipitation. But if we stay within this 1.5-degree world, which is what the politicians have said that they're going to try to and enact policies to stay within this 1.5-degree world, we could actually sort of stop this change, essentially, that we won't get this transition if we can stay within these limits. So hopefully that there's a positive message in that if the legislation goes through that reduces carbon, reduces our greenhouse gas and everything, that maybe these changes that I've talked about that might not actually come to pass, which is what we all hope for. And so quickly, just to finish off, kind of some of the key implications of this, because it's all good and well to say, oh yes, the rainfall is going to change, and I think we all know, especially living here in Winnipeg, the differences in rain and snow. But it has a very lived impact for a lot of people, both locally and it will do globally as well. And one of the kind of key impacts is what is called these rain on snow events. And I'm sure you've probably experienced it over this last few weeks here in Winnipeg, and especially those that are here in Winnipeg, where it's been warmer, we've got a bit more rain, and then it might freeze at night and it's super slippy in the day when you go out to walk. So it's quite treacherous for everybody walking around. But it also has huge implications for people who, live further north, in both Canada and in parts of Russia and Siberia and Europe, especially those that have reindeer, are reindeer herders and kind of depend upon reindeer and caribou for their livelihoods. So as you can see here, we've got this like nice snowpack, and you can see that there's 2 lines dashed in it, but you can see that there's like this layer within the snowpack, this first layer and this second layer, and that's a layer of ice. So basically what happens is when we're getting more rain falling on snow, and if it can either stay on the surface or it can percolate through the snowpack, and if it freezes in at night or at any point, this will then become an ice layer, which means that it's actually very difficult for the reindeer and the caribou to actually make their way through to forage underneath the snow, because they have to break through maybe 1, 2, even maybe 3 layers of ice. It depends on how rainy the winter period has been. So there has been a lot of instances of starvation of these animals and actually die-off. So it has huge impacts on like the local herders, so local communities that depend upon these regions. And here we're showing that these occurrences, these events occur quite frequently in certain parts, but they're going to occur a lot more frequently in the future if we're having this earlier transition, this change to a rainfall-dominated precipitation. Another key impact as well is thawing permafrost. Again, has huge implications both locally, because up in the northern regions where we have very continuous permafrost, which is the one that is basically the whole land is permafrost, it's melting very rapidly. So if you have roads there, if you have houses built on this land, they're going to subside into whenever the permafrost thaws, because it's quite solid. So it's going to have impact on people's actual houses. But it also has a very sort of global impact as well, in that when you have a thick layer of permafrost, it can store a lot of carbon. So you're not getting a lot of carbon out. But as this permafrost layer starts to deepen or get lesser, I should say, you see this red arrow is pointing up, they're getting thicker. So basically we're getting much more carbon emitted from the permafrost. And so as we know, if we're getting more carbon being emitted, that's another source of greenhouse gas in the atmosphere, as well methane. So this will contribute to our CO2 levels. So there's sort of like a negative feedback, as it were, in terms of as we warm the planet by releasing more CO2, we're going to melt these regions that store the carbon, which therefore emit the carbon, and therefore kind of this cycle goes round and round, that we're going to keep increasing our carbon. So that'll have global implications. And then as well, sort of like one sort of final key implication is the impact that it has on Greenland. So back in August this year, or last year, 2021, for the first time ever, so if we look at this region here, this orange dot in the center of Greenland, in the summit station, they had rain for the first time ever on record. So you can see that here. So they've looked at the rainfall. And that was due to this like huge increase in this big warming event across the Arctic, which meant, as you can see here, this huge melting. So everywhere where there's orange, this is the day of the rainfall event in this central Greenland region. This huge warming event contributed to a huge amount of melt across Greenland, and there was still a lot of melt in the subsequent days thereafter. But basically showing that in our results we didn't see a huge increase in rainfall in the central Greenland region, but actually the observations are showing that this has occurred. So actually, maybe we are even underestimating, which is a scary prospect, but potentially we aren't fully getting the full changes. I hope that's not the case. I hope this was just an anomaly, because weather is very variable, as we know. It's not the same every day, but basically showing that changes are happening. So, and as if we get more Greenland melt, of course, that's going to contribute to sea level rise, which will have huge global implications for a lot of cities that are sort of on the coastline. So they're going to have to either adapt or mitigate or try and find ways to lessen the impact of climate change on them. So with that, I'll finish up there. Here's sort of a few key conclusions of the work that I've been focusing on, in that precipitation has remained stationary over the last few decades, but there is going to be this greater increase throughout the 21st century, and more of this is going to fall as rain. The newer models show that there's this greater increase in precipitation and in rainfall, and a decrease in snowfall relative to the old models. And this is due to a greater sensitivity to temperatures, but with greater warming, more sea ice loss, and more transport of moisture. And therefore, on account of this, precipitation will likely transition to more rainfall decades earlier than previously projected. But on a positive note, I always try and end positively, that if we are able to stay within this 1.5 degree world, if we can reduce our impacts on our carbon emissions and everything, then we could offset a lot of these changes that could happen, and the implications that it'll have for people that both live in the Arctic and, of course, the global community as a whole. So with that, I'll finish up, and I'll happy to take any questions that anybody has. Thank you.
Thanks very much for that really interesting presentation. We have a few questions that have come through on Slido already. I'm not sure about YouTube, but Trevor will let us know. So Trevor, do you think you could pull up Slido so we can just see the first few questions that have been asked of Dr. McCrystall? And just a reminder, it's slido.com, and the password is VLFL30. If we could just show Slido on the screen. Trevor's able to do that. If not, I'll just read them out. Why don't I just start to read it out? That's all right. And then hopefully it will appear up on the screen. Okay, so I'm just going to read them in order in which they were asked. And so some of them, you may have addressed some of it in your conclusion. So what impact will rain falling on sea ice cover duration and thickness?
That's a good question, and that's one that's actually asked of me quite a lot. I haven't focused specifically, I can't say that word, on the sea ice changes, but I do know sort of some examples as well. If we're getting more precipitation into the Arctic Ocean, that's going to cause a freshening of the Arctic Ocean. Oh. And that could impact the thickness of the sea ice, in that it could trap heat within the Arctic Ocean. So you get this layer of like fresh water, and it'll trap the heat below it. In the wintertime, whenever the ice starts to refreeze, this heat then will be released. So therefore, the thickness of the sea ice, it'll not be allowed to grow as thick because it has this heat kind of melt in the sea ice below. That's sort of one impact as well. But also on productivity in the Arctic Ocean. If you're getting more rainfall on top of sea ice, that can cause, you can get like pools of water that can contribute to like more, less albedo for one, but also sunlight can maybe make its way through because it's got more of maybe it'll be thinner, but also there's more optical depth, so like the sunlight can sort of go through, if that makes any sense, go through the sea ice, and therefore allowing more productivity beneath it. So like the phytoplankton and stuff that feed kind of underneath the sea ice, which is very important then for the local the marine biology as well. So that has huge implications as well for the marine life. The duration, it might have a slight impact on the duration if it's causing that, if there's going to have to be this release of heat, as I sort of mentioned earlier. If you're having this layer of precipitation, this like fresher layer, it might impact when sea ice refreezes, which will impact the whole season and thickness as well. So it does have huge implications. It's not that I specifically studied, but there will be ramifications on the sea ice cover as well, for sure.
Okay, great. Okay, thank you for that. Okay, the next question, if we just want to pull Slido back up, is how will these changes affect the fish and wildlife in the Arctic? So, segue
exactly
to your question.
So I said it'll likely affect the productivity. You're going to get hopefully more phytoplankton, but also if you're getting fresher, it might actually contribute to less nutrients as well. So like there's kind of like there's feedbacks in all sort of sides, that if we're getting fresher layer, like we're maybe getting more sunlight into the ocean, so like allow productivity, but if we're getting maybe fresher layer, so it'll decrease the nutrient level as well. So you're kind of having this balance between. So it's very finely tuned. So it could in some regions lead to an increase in productivity, more fish, wildlife. Also as well, you're going to get warmer oceans as well. So you might get a migration of different types of fish into that region, for example, just one example. But then maybe other regions, it'll actually cause a decrease in productivity. So say it's all very regionally dependent as well, because on the Pacific side is very different to what you get in the Atlantic side, because you're getting two different masses of water from the Atlantic and the Pacific, and the kind of the circulation patterns as well. So it'll have positive and negatives, I would say.
Okay. All right. Thank you for that. Next question is, when do you expect to see Model 7 in 5 years or less?
It'll probably be longer, because CMIP 6 only came out about 2 years ago, and yeah, I'd say it'll be a couple of years yet before that happens, because it takes a long time to redevelop the models. Because I sort of said as well, like we're only modeling different aspects, and there's different things that are very difficult to actually obtain properly in the model. Clouds, for example, is a really good example of how clouds are very intricate process within the climate system. Like they go through all layers of the atmosphere, and they're all different types of clouds. So we can only model certain things, but as we get higher resolution, as we get more computer power as well, we're going to be able to resolve a lot of these, and so that just takes time and takes money, essentially. So it'll probably be the next, say, 7 to 10 years. I'd say maybe CMIP 7 might be. They're already talking about it though. Like it's already, we finish one project and it's like, right, let's get on to the next thing. But how are we going to improve? So like it's very much progressive the whole time.
Okay, great. Trevor, are there any questions that have come through on YouTube? I don't know if you wanted to put one up on the screen, if there's anything that's come through YouTube. I just want to make sure we're answering questions that way as well before we go back to Slido. If you're able to post. If not, we can go back to Slido, which is just fine because there's lots of questions there. Okay, so let's return back to Slido then. Okay, so is there a difference in the predicted increase in precipitation between the terrestrial and marine Arctic region?
There would be. I haven't broke it down that way. That's a really good question. But there definitely would be, in that. And it depends seasonally as well. Like this is the thing about the Arctic. There's so many areas that there's just so much that makes it very variable, because you've got this ocean, you've got this land, and you've got per season as well. But I think over land, you get much more precipitation over land than you do over the oceans, which probably is counterintuitive considering the fact that you get more water in the Arctic Ocean. But you think about storms and things like that, they occur more over land. Like they can't really propagate as much and as far into the Arctic than they can across land. So you will get much more precipitation on land than you will over the ocean. Well, so one of the first slides I was showing was like the spatial variability, and you could see over the Atlantic, there's much more precipitation over the Atlantic. But in just terms of like the 70 degrees North Arctic, Most of it will be, in comparison to the Arctic Ocean, most of it will be over land compared to that ocean. But the Atlantic Ocean, or the sort of at the edge of the Arctic, you'll get much more precipitation there because of the fact that that's where a lot of the storms kind of propagate into. But yeah, just like Arctic Ocean and land, it will be over land.
Mm-hmm. Okay. Another question that was a follow-up from Slido is asking specifically how this will impact polar bears.
I'm not sure. That's my most honest answer. Because the biggest sort of change in polar bears will be sort of their ability to get around on sea ice. So precipitation, so the kind of like non-linear way around this would be if precipitation affects.
Oh, you froze there for a second.
But yeah.
Sorry, Michelle, we missed that. Do you mind saying that again?
Yeah, because it froze on my side too. So as I said, I've never really focused on polar bear change, but sort of my best guess would be that it will impact polar bears, because if we're getting precipitation change, if it impacts the sea ice, which is where polar bears will hunt from, if that's impacting them, then it will have a negative impact on polar bears. It might push them further inland if there's going to be less sea ice. I'm not sure in terms of like rain on snow events if it'll impact them that way, because they're meat eaters, more so than having to actually forage, for example. Mm-hmm. But it will be more of the precipitation's impact on sea ice and what impact that will have, and like on the land that the polar bears are able to get around.
Okay. All right. I'm gonna ask one more question, and if you're okay, we do have more questions that have come
through. Yeah.
Maybe I can send them to you, and then we can share them with all of our attendees for today. I'm gonna pick the one that says, "Please explain the 1.5 degree world in detail." If you could talk about that you mentioned at the very end.
Again, this is out of my wheelhouse for sure. I don't really focus on the policy. I don't know what the politicians have said we need to do for 1.5 degree world. Well, I know the sort of general, I think everybody knows the general, we need to reduce our carbon emissions, mm-hmm. But what a 1.5 degree world would look like, I honestly can't say. What I would like it to look like would be more focus on public transportation, getting people out walking, maybe less dependence on aircraft, but also I think that's a big ask, if I'm being honest, someone who's an international person here in Canada. But I think we'll have to transition the way that we use aircraft. Like there are studies going into like hydrogen aircrafts and other ways of being able to fuel aircrafts, because that is like a huge contributing thing. But I think one of the biggest things is transitioning away from fossil fuels. Like that's going to be the biggest change, because during COVID actually was really interesting time for climate scientists, because some studies were done, and like I'm only quoting what I have briefly read, but they have shown that yes, there was a decrease in CO2 emissions because you had no planes traveling and things like that, and you made less cars on the road, but there still was carbon emissions occurring, and a lot of that was due to like big businesses and things that contribute that. And it really showed actually that it's not just, people think, oh, we need to stop being on airplanes, and yes, that's one factor, but the way that we heat our homes, the way that we heat our businesses, the way that huge organizations transport, like everything kind of has to really transition quite rapidly, because like we're already at 1.2 degrees, I think. So it has to be a very rapid shift, a very quick transition. And like I don't have any off the top of my head, but there are really innovative people around the world who are finding new and amazing ways in which we can fuel our economy and fuel our world. That takes us away from use of fossil fuels. I think there still will be a dependence for the next maybe 10 years, if I'm honest, at the very least 10 years, because, you know, it's a slow transition because it's everything that we live with, depend upon, was based on the fossil fuel emergence, essentially. So there will be this transition, but basically, I think that's kind of what the 1.5 degree world is. It's like Green New Deal. I think there's a lot of positives in it, because people are like, oh, well, what about jobs? But we can retrain people into living in a green world. Like, you know, people had to learn how to go out on oil rigs, but we can teach them how to, I can't think of a good example, like install wind turbines or solar. So I think, I know I tend to be a positive person when it comes to climate change, or try to be, especially because I look at it every single day. but there is positives that can come from it. We can get new economies, new growth. Because I know economists will say we need to keep continuing to grow. This is not my area, economy at all. I just look at the science, but yeah, I think rapid, quick transitions to less fossil fuel dependency.
Okay. Well, that's a great answer and lots of takeaways there. And I think that would be another really interesting topic is the economics of climate science and climate change and what does that mean, and moving more into what you're saying. But thank you for your thoughts on there. I realize that your focus is on the science aspect of it. So, but anyways, I think that's all the time we have for today. As I said, there's some more outstanding questions that we'll make sure to send you, Dr. McCrystall, and then when we send our evaluation and the recording of the session with all of our registrants, we can include that information there. We did the same with the dean last week. So again, we'll be sending you a survey to everybody who attended. Please do fill it out. It's the only way that we're able to improve and that we're able to take your feedback and invite other researchers, postdocs, and professors to speak on other topics. If you haven't registered for next week, so again, remember this is our climate series, our spring climate series. Next week, we welcome Dr. Karen Alley. She's also from the Center for Earth Observation Science in the Department of Environment and Geography in the Clayton Riddell faculty. And her topic is on the future is unstable, studying the world's great ice sheets and glaciers to understand sea level rise. So another topic similar but different than what we've heard from Dr. McCrystall today. So if you have not registered for that, I highly encourage you to do that, whether you're able to participate live or want to watch the lecture after the fact. Thank you again, everyone, for participating, making this part of your day. Check out our website with previous sessions, and I hope to see you next week. Thanks very much.